Okay, here we are. It's a real pleasure to be here, especially because in my research career I spent quite some time on the research on the SNARC effect. In fact, my first SNARC experiment led to a positive result from the first time back in '94, and you can see it displayed there. Now, my last published SNARC result is from 2011, and as you see, there's not much difference between the two time periods. Now, in fact, if you look very carefully, there is a big difference, namely what's on the x-axis. In '94, and still quite some time later, there was the number magnitude on the x-axis, and from 2011 we have put something else, namely position in the sequence on the x-axis. With position in the sequence, I mean position in working memory. And I'm going to describe this trajectory from long-term representation of numerical magnitude to our position, that it is position in a working memory sequence that drives the SNARC effect. So, in the beginning, the classical explanation of the SNARC effect is the mental number line hypothesis. As already indicated, there's a long-term spatial representation of number magnitude which takes the form of a mental number line. And interestingly also is that it has often been assumed that there is a functional isomorphism between number space and physical space. It is as if the characteristics of the spatial coding of the mental number line uses the same metric, namely a coordinate-based system, as the representation of physical space. And finally, there's also the assumption that there's an involvement of a common mechanism for orienting spatial attention. Now, to display this a bit graphically, the situation is simple. The SNARC effect is a bit like the Simon effect. When something is presented on the right side, and you have to give a right response, that's a congruent situation. When something is presented on the right side, and you have to give a left side response, that's incongruent, takes more time. The same thing happens when with the SNARC effect. A number is situated on the right side of this spatially oriented mental number line. A right side response is easy. A left-hand response is difficult. So, a functional isomorphism. Now, in a first series of studies, we started to investigate whether or to what extent we have to assume that the characteristics of this spatial information really takes the form of a coordinate-based system, or has the same metric as the way we represent physical space, because there are also other ways to present or to represent spatial information. We can use verbal labels for it, for instance, left, right. Correspondingly, we can speak of small numbers, large numbers, or we can have left, middle, right. It doesn't have to be binary. You have small, medium, large, extra large, and so on. These are verbal labels which don't necessarily imply a coordinate-based system. There have been many instances of this hypothesis. There's Proctor, who had a specific hypothesis and applied it to the SNARC effect, where he assumed a binary coding of numerical information, but also spatial information, and all kind of dimensional information. And his polarity coding assumption assumes that there's a positive and a negative pole. Left is negative, right is positive, just like small is negative and and large is positive. And that he assumes that the SNARC effect follows from a congruency overlap on these binary dimensions. But also Coslin he proposes distinction between the processing of spatial information into distinct ways, the coordinate-based and the categorical. Pavio, an even older theory, he has the dual coding theory, specifying that we can represent our environment in two ways. We have one analog to sensory motor experience, the other is a verbal way of describing reality. Now, with Wim Gevers, who is present here, this idea was incorporated in a computational model, and I'm not going into the details, but essentially, the crucial thing is that this model assumes that numbers are categorized as being either small or large. And this model, together with all the other parameters and assumptions that are there, can give or can generate results that pretty much resemble the empirical results, as you can see here. Again, I'm not going to go into the detail, but just show that it is possible that a binary categorical classification of number as small or large can generate a SNARC effect in very good detail. But of course, such a computational model, that's no proof of existence, or it's not a proof that the reality is like that. And therefore, based on this work, we developed a research program. And the first thing we wanted to investigate was the following. Now, let's remove all references to the physical space in the design of the experiment. So we do a SNARC experiment. Numbers are presented centrally, and we remove lateralized physical responses left or right just by asking subjects to say left or to say right as a function of the parity status of the number. In the same subjects, we tested the SNARC effect in the traditional way, and what we find is a very nice overlap between the two versions of the SNARC effect, one obtained with verbal responses, the other with manual responses. So the SNARC slope didn't differ, and if you look at the individual data points, it's quite similar. So this experiment shows that it is possible to generate a SNARC effect based on verbal information. But then in the next experiment, due to a very clever idea of Wim Gevers, he developed a design where it was possible to really pit against each other the conceptual versus the physical space explanation. The idea was, in this case, that subjects didn't have to respond or didn't receive the instruction to respond either with the left hand or with the right hand, but they were instructed to press a button that was variably labeled left or right. So they had to press the button which was named left or which was named right. And then, of course, the label left could be on the left, but the label left could also be on the right. But subjects had to press the button bearing the label, not the side in space. Now, in a congruent situation, where the position of the word corresponded to the physical position, there the predictions of the physical account and the conceptual account are exactly the same, a normal SNARC effect. But when the position of the words is incongruent, the position or the prediction differs, and the physical account says that for a small number, there will be an easier response on the left side, or the right side with the left or the right hand. But for the conceptual account, the prediction is the opposite. In fact, it is predicted that there will be a reversed SNARC effect in this situation. So the question is, does the SNARC effect follow the position of the hand or the position of the label? And what we observed was clearly in the dotted line here, you see the reversed SNARC slope, meaning that the SNARC effect followed the words, not the position of the hands. being in line with the prediction of the conceptual account. In a magnitude comparison, where subject had to press left or right, again on the buttons, we observe exactly the same thing. So when we put these things together, we come to the conclusion that the spatial coding underlying the SNARC effect doesn't have the same metric as the visual-spatial representation of physical space. And that it seems to originate from a more abstract level of processing, be it binary as a classification of small, large, and left, right, and the way these are associated, or at a more refined level where there's categorical spatial coding, left, middle, right, small, medium, large, and so on. Now, of course, the fact that we now have an indication what type of information drives the SNARC effect doesn't explain really the mechanisms that underlie it. And to address this question, we focused on which we felt an important and at the time somewhat overlooked finding or set of findings, namely that the number space associations are more flexible than one would expect from a long-term mental number line representation. First, as already indicated by Stan, there is a range dependency. A number 4 and 5 is large in the range 0 to 5, but is small in the range 4 to 9. There's also a strong dependence on visual imagery, as shown in a study where Peter Brugger was involved, because he showed that when people are required to imagine numbers on a clock face, that the large numbers induce preferentially left-hand responses. And there's, as indicated by Sam Shaki in the previous talk, there's a the SNARC effect flexibly depends on reading habits. Reading just before a paragraph from right to left can really reverse the SNARC effect. So this seems to suggest that the spatial coding involved in number is not inherently associated to number, but that it is constructed during task execution, suggesting a crucial role for working memory. And in a first set of experiments, following on the work of Herrera and Semenza, we tested this idea in 2 tasks, parity judgment and magnitude comparison, with a visual-spatial working memory load and a verbal working memory load. What we did was first test the baseline SNARC effect, so no working memory, explicit working memory involvement whatsoever. Then we tested working memory span either in visual-spatial or verbal working memory. And then we went to this experiment where we preloaded working memory at the span -1 level with a Corsi-like situation. And then during the retention interval, we tested the SNARC effect, be it parity judgment or magnitude comparison, and then afterwards there was a reproduction phase. Similar for verbal working memory, where letters were used to load working memory. Now, with the magnitude comparison task, we observed that the SNARC effect disappeared under visual-spatial load, but was preserved under verbal load. During parity judgment, on the other hand, we found the opposite, namely that the verbal load abolished the SNARC effect, but nothing happened with visual-spatial load, indicating that, to some extent, free working memory resources are required for the SNARC effect, but that these differ as a function of the task. Namely, for magnitude comparison, we need visual-spatial working memory resources. For parity judgment, we need verbal working memory resources. That's already an indication for the involvement of working memory, but of course, this doesn't really explain the mechanism. So the question is, how can working memory account for the SNARC effect, with the emphasis on how? Now, we started from the following hypothesis in this line of research, namely two ideas. First, when subjects perform a task, in fact, for every task, they will create a task set, which type of stimuli, which type of responses, which response do I give to which stimuli, and store this information in working memory. Now, by using numbers, it could be efficient to use this numerically ordered information to have easy access in working memory, maybe to expand the capacity of working memory, and so on. And a second hypothesis was that maybe the spatial associations we observe in working memory derive from the fact that items from the beginning of a working memory sequence, that they are associated with the left, final items associated with the right. And that's the hypothesis we set sail for investigating. In this experiment, we had a numerical preload, so we asked subjects to keep in working memory a series of numbers, not in numerical order. So for instance, 7, 3, 9, 4, 1. Then during the retention interval, subjects had to perform a parity judgment task in this case, but it was a go, no-go version of the parity judgment task. So they only had to respond when the number presented during the retention interval corresponded to a number that was maintained in a verbal working memory sequence, to make sure that they would access this this information in working memory. And then afterwards, there was a recognition interval. In this case, subjects had to select the correct sequence here, the correctly ordered sequence here. Now, the results show that it is clearly the position in working memory that is associated to the left and the right response, confirming the predictions that items from the beginning of the sequence prefer a left-hand response, items towards the end have preferably a right-hand response. Of course, we can also look at the numerical magnitude, but we didn't observe any sign of a residual effect of number magnitudes whatsoever. Then, in a second experiment, we thought, well, maybe if this is true, then we even don't need numbers to generate a SNARC effect. We can use whatever type of information which we store at a certain position in working memory. We tested this idea by presenting names referring to particular fruits or vegetables. And during the retention interval, there was no parity judgment task, of course, but in this case, a fruit-vegetable categorization task. So subject had to keep in memory apple, lettuce, pea, onion, cherry. During the go, no-go fruit-vegetable categorization, they had to categorize as fruit or vegetable once they saw one of these fruits or vegetables presented. During recognition, subjects had to judge whether the items were presented in correct order. Note here that this was also a second purpose of the experiment, that we presented the items successively on the screen to obtain a situation devoid of any reference to spatial information. The results show that indeed we can obtain a SNARC effect, although it's better not to call it like that because there's no reference to number in this case, with fruits and vegetables. Again, fruits or vegetables from the beginning of the working memory sequence, preferentially left-hand responses, towards the end preferentially right-hand responses. Interestingly, in the very same subjects we tested here, we also tested the SNARC effect with numbers, with no reference to working memory, just a regular classical parity judgment SNARC effect. And what we found was that the positional fruit-vegetable effect significantly correlated with the size of the number SNARC effect in a parity judgment task without making any reference to a number. So the conclusion of this study then is that it's really the temporary position space associations and not the long-term ones that drive the SNARC effect. Meaning that in normal situations, that's our hypothesis, that we assume that people spontaneously, to optimize performance, use their working memory, store the information. This number was, number 1 was a left-hand response, number 2 was a right-hand response, 3 left, 4 right, and so on. Now, this mechanism provides a unitary explanation for a number of phenomena which are not straightforwardly explained by a long-term explanation of the mental number line. For instance, the dilution of the SNARC effect under working memory load, that's evident. The SNARC effect, even when number magnitude is completely irrelevant for the task, von D monitoring, is there an E sound, yes or no, in the number presented? With the working memory account, it's easily explained. The range dependency, that's if you only work with the numbers 0 to 5, then 4 and 5 are positioned in the later regions of the working memory sequence. When you work with 4 to 9, they come at the beginning. There's the dependency on, also the dependency on imagery is the way you put information in your working memory. Basically, we test the same idea here. The rapid changes of direction of the SNARC effect can also be explained in this case, although it requires additional assumptions. And also the SNARC effect with non-numerical ordinal information like letters of the alphabet, newly learned ordered series, musical tones, and so on, can be explained by this working memory account. Now, in a very recent series of studies, we wonder to what extent spatial attention is operating in this, let's call it, workspace. Again, we use the same task structure, numbers in working memory, not in a numerical order, but in arbitrary order. And then we applied Martin Fisher's Posner-like paradigm, so the numbers acted as a cue. And it was also in a go, no-go situation when the number belonged to the working memory sequence, subject had to give a response when a probe was presented. And afterward, accuracy of working memory was tested. We replicated this 3 times, 2 times with key presses, and a 3rd time also with verbal responses. Subject didn't have to press a key when they saw a probe, but they just had to say yes whenever they saw a probe appearing. And what we observed 3 times was a significant position space association. More work on this is presented on a poster, which I think is interesting to further look at. So it's additional replication, so the effect that was sometimes difficult to replicate, if you use position in working memory, it's really, really robust and replicable. And then finally, a few words, if I still have time, on the neural basis. Now, although we have all the means to do fMRI, and although I'm interested for a long time in the SNARC effect, we never really investigated directly the SNARC effect. Because, as I said, in fact, it's a kind of a conflict task, and it's very difficult to control. It's not impossible, as Stan already showed, to avoid the pitfall of demonstrating response conflict-related phenomena. We took a different approach, and a theory-driven, and we wanted to look at how number processing relates to working memory processing and partly also to attention. Now, if we look to a typical situation, comparing numbers, comparing other ordered series, I'm not going into the detail, but what's important here is that there's a parieto-frontal network that underlies these number or ordinal comparisons. If we look at order processing in working memory, this is a bit of an older study in which we looked at working memory of non-words or of faces, there were two task conditions, so subject had to remember a series of faces or a series of non-words, and then were asked to judge the order of two faces or the identity of two faces. Same thing for non-verbal information. And then what we see is that for faces, but also for non-words, the order task induces activations, parieto-frontal circuits, much like in the normal number comparison. Of course, this is very, very indirect evidence, but in a recent study of Lucie Atou, who is also here, the issue was addressed directly whether there's any overlap between serial order in working memory and number processing. So what she did was she had an ordinal number judgment task, basically a number comparison task where subject received a two-digit number and they had to indicate whether it was smaller or larger than 65. There was an order short-term memory task. So the subject received a series of letters to keep in memory and then received an order judgment task. Is this the correct order from top to bottom to avoid spatial confounds? In the two tasks, distance was manipulated, and that's what was looked at. So small and larger distances. And then finally, there was a control task. Subject received a series of identical letters, and then had to perform a luminance decision task. Is it the same luminance, yes or no? And the luminance could differ along two distances. Behaviorally, distance effect was observed in the three situations. And when we look into the brain, we see again the bilateral hips with some frontal activations, much like we saw before, were the result of the conjunction analysis of the distance effect in the ordinal number task, in the number task or in the order short-term memory task. Voxels obeying to a distance effect in the luminance task were eliminated from this conjunction. So this is only order in working memory or number. And then in another study, we try to establish to what extent the workspace involves the operation of spatial attention. And for this study, we used the fragmented trial design in the context of a numerical landmark task. In this task, subject received two numbers. Then those numbers were erased, and then there was a variable duration interval. And then, on a certain moment, they received a probe, and subject has to judge whether it was numerically closer to the left or to the right number. We had a baseline, I don't know, control, whether you can clearly see it. On the moment that the probe was presented, there was a thing that could be a circle or an ellipse, and subject just had to indicate whether it was a circle and an ellipse. And we could vary or make the task more difficult to equate performance to the numerical task. We also had a color landmark task to provide additional control. And what you see displayed here is the result of the number landmark task compared to its situation. And then we see that the anterior part of the intraparietal sulcus was exclusively activated during the maintenance interval, whereas the more posterior, displayed in green, became active only when the probe was presented and the response could be prepared. Now, another interesting thing is that the anterior IPS was not activated during the number task, whereas the posterior part seems to be a more general purpose area, because there was a clear activation as soon as the color probe was presented. Now, of course, this doesn't by itself say nothing about spatial attention, because many things can happen here. But we also included an attentional localizer based on the retro-cueing paradigm developed by Nombre. Basically, the situation is quite easy. Configuration of 4 colored X's is presented. Then a cue is briefly flashed to either of one of the 4 corners where an item is displayed. And then, in the end, subject receives a probe and has to judge whether it belonged to the original display, yes or no. This is a situation of an informative cue. This is a situation of a non-informative cue. Now, this task was only briefly presented, and we had hoped that the contrast informative versus neutral cue would have been enough. But unfortunately, this was not the case. But then we resorted to a multivoxel pattern analysis and asked whether a classifier, and in which region, would be able to distinguish between informative cues versus uninformative cues. And we applied this classifier to the 2 red regions, the anterior IPS regions, and also to the 2 green regions, the posterior IPS regions. And what we found was that a classifier couldn't do the task in the anterior regions, but could do so in the posterior IPS regions, suggesting that these posterior IPS activations are related to attentional orienting, this case in mental representations stored in working memory. So as a conclusion of this study, there's overlapping frontoparietal neural networks for number processing and processing order in working memory. There's an involvement of the anterior IPS during maintenance, storing information, and posterior IPS once you start to operate on this stored information, probably related to spatial attention. And then in terms of the general conclusion, our studies reveal that the spatial representation of the SNARC effect, that they are of a more abstract and categorical nature, that the interactions between number and space occur at the level of working memory, and more speculatively and hypothetically, I would like to propose as an idea for further research that working memory might also be the convergent point of space, time, and number. Because in my opinion, when one looks at the interaction between number, space, and time, it's always difficult to see how to map from one dimension to the other. 1 second, why would it map to the number 1? And maybe it does so in some situations, but in other situations, 1 second is the shortest duration, then it should correspond to 1, but sometimes it's the longer duration, and then it should correspond to the number 9, and so on. It's really depending on the situation, the task at hand, that empirical phenomena like congruency effects between the dimensions are observed. And I would propose that it is not something which is stored in working memory, but that in long-term memory, but that there's a mapping to working memory and the positions therein that generates the effects. And in this sense, the serial position provides a possibility to calibrate one dimension or to map one dimension on the other. And of course, there are also remaining questions. What about the number-space interactions in the other tasks? To what extent does, for instance, number bisection, the operational momentum, pointing, and so on, to what extent is it long-term numerical meaning or short-term position in working memory representing the numbers you are working with at that time is the important factor. Thanks to my collaborators and to you for your attention.